It's a pleasure to introduce today's speaker, Kristin Courtney from Münster, who will speak on generalized inductive limits with asymptotically order zero maps.
Okay. Yeah, so many thanks for the introduction and for the invitation to come and speak. I'm really excited to be a part of these global NCG seminars. I think it's really, really exciting that we're keeping up a good, robust connection for researchers around the world. So I'm really happy to be part of it. It's actually the second time I've spoken in one of these seminars, but I've been speaking on the same joint project with Wilhelm Winter. But I'm going to give, so I gave a talk on this work in the Americas NCG seminar, oh gosh, must have been a couple of months back. But so I decided that for this talk, I want to give a talk about the same material, but with a different perspective. So this is on generalized inductive limits with asymptotically order zero maps. And I think I noticed my collaborator in the audience, so he's here to correct me if I say something out of line. Okay.
That's not why I'm here.
Okay, so right, so let's just start with the basics. Inductive limits of C-star algebras. So a definition that I assume everyone has at least seen before, an inductive system of C-star algebras consists of a sequence of C-star algebras together with connecting star homomorphisms. And for each K, the quotient map, which sends the space of norm-bounded sequences coming from elements in these C-star algebras to the quotient of this space by the sequences that converge to zero in norm. This induces a star homomorphism from each of the C-star algebras in the sequence into this quotient space by simply just taking, for any C-star algebra AK in the sequence and an element in AK, you just look at the string of its images along the sequence. This will form a bounded sequence, and just look at the image of this in the quotient. And this is, roughly speaking, the way that we prove that inductive systems of C-star algebras always have an inductive limit. And the inductive limit of the system is the C-star algebra, which is where you take the union of all of these images and then you close them up. Now, this construction is well, it's a very important construction in the area of C-star algebras. And one reason it's provided a lot of interesting examples of C-star algebras. So for instance, approximately finite C-star algebras, which arise as inductive limits of finite dimensional C-star algebras. AT algebras, which are inductive limits of direct sums of matrix algebras over continuous functions on the unit circle. And approximately homogeneous or even subhomogeneous algebras, which are limits of homogeneous C-star algebras, which we'll take for this talk to be corners of matrix algebras over continuous functions over some compact Hausdorff space. But not only do inductive limits of C-star algebras give us interesting classes of C-star algebras, if you can realize that a C-star algebra that you've encountered out in the wild is actually an inductive limit of C-star algebras, this can disclose a lot of information about the structure of your C-star algebra. So a collection of sample theorems would go as follows. So if we take a simple separable unital C-star algebra A, then it fits into the Elliott classification program, meaning that it's in a class of C-star algebras that can be distinguished via their K-theory and traces, provided that it's either AF. So this was Elliott's first foray into the classification of C-star algebras and was meant to be a direct analog of the classification of hyperfinite factors. But then it turns out that the classification results in C-star algebras pushed beyond AF into the AT algebras, provided that they have real rank 0, which means that the invertible elements are dense in the self-adjoints. And this really kickstarted the classification program, especially when Elliott and Evans proved that one could actually realize irrational rotation algebras as these guys. And another class, going back to the AH, is the AH C-star algebras with real rank 0 and slow dimension growth. And this refers to the dimension of this Hausdorff space X, with which we defined the inductive systems. And the slow dimension growth is basically exactly what you need to stave off these counterexamples from Andrew Toms for the classification program. So this is the classical setting of inductive limits with star homomorphisms. And working with these inductive systems, one realizes that on-the-nose behavior at each step is often, if not always, superfluous. And the real mantra that one should take is that asymptotic behavior is really what matters. And following this philosophy, Blackadar and Kachberg introduced these generalized inductive systems of C-star algebras, where the connecting maps are no longer star homomorphisms, but only asymptotically behave like star homomorphisms. So they actually go through and systematically weaken each of the basic properties of star homomorphisms, linear, star preserving, multiplicative, into an asymptotic setting. I'm not going to address their constructions in full generality. Oh, forgot to mention, they also show the limits of these systems form an important class of C-star algebras, right? So I'm not going to talk about the full generality of their constructions, but I'm going to focus on the so-called NF systems. So an NF system consists of a sequence of finite dimensional C-star algebras together with asymptotically multiplicative, completely positive contractive maps. So before I address asymptotically multiplicative, to make sure we're on the same page, just quickly, completely positive contractive maps between C-star algebras. This is a natural class of maps for us to consider. They are, in a sense, much more abundant than star homomorphisms, but still very good at preserving structural properties for our C-star algebras. So a map between C-star algebras is positive when it maps positive elements to positive elements. And it's completely positive when this stays true under matrix amplifications. And contractive just simply means norm decreasing or norm less than or equal to 1. So by asymptotically multiplicative, what I mean is the following, that for any of these FKs in the sequence, if I take 2 elements in FK and some tolerance epsilon, then if I go far enough down along the sequence, and once I've passed a certain threshold M, then if I take the image of X and the image of Y in the nth term in this sequence, and in a sense, remember, we're identifying, especially in the limit, we're identifying X and Y with their entire sequence of images, right? So I take X far enough down in its sequence of images, and the same thing for Y, and then when I multiply them, then the next maps are pretty close to being multiplicative. Now, this is a little more complicated than the naive attempt, which would be where you just want rho mk for little m sufficiently large, rho mk of x times rho mk of y to be close to rho mk of xy. But it turns out that's a little bit too strong, and it goes against this idea that we don't want on-the-nose behavior at any sort of finite step. But so we form the inductive limit of an NF system really pretty much the same way as before. We have induced maps from the finite dimensional C-star algebras, which are now just going to be CPC, but still we take their images and close them off, and we call this a NF system. Now it turns out, since this quotient only really cares about what happens asymptotically, this asymptotic multiplicativity comes together in the limit and actually gives us an algebraic structure. And we get a C-star algebra, which is called an NF algebra. Now, one reason this class is particularly interesting is Blackadar and Calgebras showed that separable C-star algebra is NF if and only if it admits a completely positive approximation with asymptotically multiplicative maps. So what does that mean? So that means that we have, in this case, a sequence of finite dimensional C-star algebras and CPC maps going from my C-star algebra A, factoring through these finite dimensional C-star algebras, so that, first of all, the first criteria that we see here is saying that the composition of these maps converges pointwise in norm to the identity map on A. And the second condition is the asymptotically multiplicative condition. Now, blurring the asymptotically multiplicative part, we actually have the definition of nuclearity for a C-star algebra. So in particular, or at least the completely positive approximation property, which is thanks to Troy and Calgebras, we know this is equivalent to nuclearity for a C-star algebra. And many times when you see these presented in talks, we like to describe them with this pretty little approximately commutative diagram, which I'll bring up again later for illustration. But in particular, we know these are nuclear. And moreover, what Blackadar and Calgebras actually show is that the NF C-star algebras are exactly the separable nuclear C-star algebras, which are also quasi-diagonal. So quasi-diagonality, so a C-star algebra, thanks to Voiculescu, we can say that a separable C-star algebra is quasi-diagonal if it admits what I would say called a separating family of almost representations, meaning that you have CPC maps into, or finite dimensional representations, which means that you have CPC maps into finite dimensional C-star algebras, which are asymptotically multiplicative, so they're close to being finite dimensional representations, and asymptotically isometric, which means that they are separating. I see I have a question in the chat. I will address that later on. Okay. Okay, so the question is, what if we just want to get at nuclear C-star algebras? So to do so, we have to relax this asymptotically multiplicative assumption. This is really intimately tied in to these NF C-star algebras. But this asymptotically multiplicative assumption also wrapped in quasi-diagonality. But the problem is without asymptotic multiplicativity, the inductive limit fails to be an algebra. So we need to somehow relax multiplicativity without losing the C-star structure. Okay, so enter order zero maps. So we say a CP map between C-star algebras is order zero if it is orthogonality preserving. So that means that if you have two positive elements that multiply to give you zero, then they multiply to give you zero in the image as well. So Venter and Zacharias had a really influential paper working with these order zero maps. And one of the key results in this paper is the so-called structure theorem for order zero maps. And here is an oversimplified version of it where we assume that the domain C-star algebra is unital. So a CP map from a unital C-star algebra is order zero exactly when it's almost multiplicative, except one has to pay the penalty of multiplying by the image of the unit. And note that what this says is that if we have a unital or a unit preserving CP order zero map, then it's automatically going to be a star homomorphism. So many times when we're working with order zero maps, for non-triviality reasons, we're implicitly assuming that they're not actually going to be mapping units to units. Okay, So these are a natural step down from star homomorphisms, and they actually retain a lot of the same nice properties that you get from star homomorphisms. So we know from a theorem of Wolff that if we have a CP order 0 map from a unital C-star algebra, then the image of the unit commutes with the image of the C-star algebra, which of course is trivial for star homomorphisms. And then the next is, again, from the same paper of Venter and Zacharias, where they show that if you have a CP order 0 map, then all of its matrix amplifications are also CP order 0. In other words, an order 0 map is completely order 0, automatically. And what one can also show, going back to the orthogonality preserving definition of CP order 0, is that if you have an injective CP order 0 map, then just by being CP, we know that it's sending all of the positive elements of A into the positive elements of B. But what this is saying is that if it's an injective CP order 0 map, then if I take any element X in A and its image was positive in B, then I already know that X was positive in A. So taking that along with this proposition from Venter and Zacharias, we can say that a CP order 0 map that is invertible on its image, it automatically has a completely positive inverse. Okay, but what's more, a CP order 0 map actually really leaves an impression of its structure in the image, even to the point that we can detect when a self-adjoint subspace of a C-star algebra is the image of some CP order 0 map. I'll get back to that in a little bit. But first I have to actually address this bit. The preserved structure is actually enough to really allow us to build a C-star algebra out of the image outright. So I need to highlight exactly the properties of a CPC order 0 map I'm going to be using here. So let's take a CPC order 0 map between two C-star algebras where the domain C-star algebra is unital. And for simplicity, I'll write X for the self-adjoint subspace that's the image of A, and E for the image of the unit. And then we have the following. So from the theorem of Wolff, we know that E commutes with X. From rewriting the theorem of, or the structure theorem of Venter and Zacharias, we can say that X squared is equal to EX as sets. And this is just simply saying that for any A and B in A, psi of A times psi of B is equal to the image of the unit times psi of AB. And lastly, E is an order unit for X inside of B. And that bit I need to define. So taking some inspiration from Choi and Efros's work on abstract operator systems, given a self-adjoint subspace of a C-star algebra B, we say a positive element E in X is an order unit for X if for any self-adjoint element in X, there's some positive number R. So if I scale E up by R, it will dominate X. And more specifically, I'll say that E is a uniform order unit if that R that I could have chosen was just the norm of X. And a good example of this, and sort of the paradigm example of this, is just the unit of a unital C-star algebra. And then this inequality here is a very basic fact about C-star algebras. More generally, this notion also works even when there's no unit around. So just consider this copy of the complex number sitting inside of the continuous functions on the half-open interval. It turns out that the identity map is still going to be a uniform order unit now for this subspace. And that idea generalizes even more. If we just take a unital C-star algebra and we look at its canonical image sitting inside of the cone over A, then the tensor product of the identity map along with the unit for A forms a uniform order unit for this subspace. And even more generally, if we just have a CP map, then from a unital C-star algebra, then the image of the unit is an order unit for the image of the C-star algebra. And it'll be a uniform order unit provided that the map is CP order 0 and isometric. Okay, so this is the notion of order units. And now going back to those.
May I ask a question about this? So you said something about the identity.
Yeah.
How should I read that? The identity on the.
Yes. So that's right. Thank you. The identity map is just simply, if you consider the continuous functions on 0, 1, this is the map that sends Z to Z.
Okay, in that sense, yeah, sure.
Yeah. Okay,
perfect. Yeah, thanks.
Yeah, this is a good toy example. So I want to make sure that everyone has that picture. All right, good. So these 3 criteria that I highlighted a minute ago are actually enough to define a pre-C-star structure on a self-adjoint subspace of a C-star algebra. So this is exactly what I mean by that. So let's take a C-star algebra B and a self-adjoint subspace and a positive contraction sitting in the C-star algebra B. And let's suppose that they satisfy these 3 criteria that we highlighted before. E commutes with X, and it's actually in X. X squared is equal to EX, and E is an order unit for X. Then it turns out we can define an associative bilinear map on X so that X, along with this, I'll call it bullet multiplication, is actually a star algebra whose unit is now going to be E. Now, when X is actually the image of a CP order 0 map, then this is really, this is coming really directly from the structure theorem for order 0 maps. And in particular, this little bullet norm, hold on a moment, let me finish this, what I was just saying. Right, so if X is the image of an order 0 map, then basically we can think of this multiplication as just remembering the multiplication back in A. In general, we can't always say explicitly what this is, we just can say that it exists. But we can say that it's going to satisfy this equality here, which looks a lot like the structure theorem for CP order 0 maps. So in particular, if I multiply 2 things, and this multiplication here is in B, and then I take E, and I take the multiplication in B with X bullet Y, then I get this equality here. So I have a star algebra structure, but moreover, we can also define a pre-C star norm on this star algebra. And because when you have a pre-C star norm, there's a good question about exactly what does the closure look like. And one case where X is already complete with respect to this norm is when it's actually already closed in the C star algebra B that it's sitting in. So I went through this theorem a lot more in my Americas NCG talk. And so for this talk, I'm going to mostly focus more on the results instead of how we get there. So let me just pick up some of the more important results from this little subsection here. So given a self-adjoint subspace X of a C star algebra B with a distinguished positive element in positive contraction in B, we abbreviate the criteria that gave us the pre-C star structure on X just with the term parentheses C star. And so that means that when X and E satisfy C star, then we can define multiplication on X and a pre-C star norm on X, meaning exactly that if I complete X, when I'm thinking of it now as having this bullet multiplication, I get a C star algebra, which I will call X bullet, just to distinguish when I'm assuming it's got this multiplicative structure and when I'm assuming it's just a subspace of B. So one question is really, what is the relationship between the structures X as a subset of B and X as a subset of this X bullet? And it turns out that if we have a self-adjoint subspace X of a C star algebra B with a distinguished positive contraction that allows me to build this C star structure, it turns out that if I take the identity map sending X as a dense subspace of X bullet to X as just a subspace of B, This extends to a CPC order 0 map between the two C-star algebras. And in fact, we can say more. And this is what I was alluding to before. The following are equivalent for a self-adjoint subspace of a C-star algebra with distinguished positive contraction in that C-star algebra. And the first is just that X is the image of a unital C-star algebra under some CPC order 0 map that sent the unit of the C-star algebra to this distinguished order unit E. And that's equivalent to saying that the pair X and E satisfies C star, and moreover, X is closed with respect to this bullet norm that we can define, which you should think of as saying that X and X bullet are equivalent as sets. Taking this closure doesn't add anything to X. And so this actually means that when I said before that a CPC order 0 map really leaves an imprint of the structure on its image, this is what I meant, that we can really just pick up from the image that it was the image, or we can just pick up from a self-adjoint subspace that it was the image of a CPC order 0 map. And we can actually even say more. So if we take a unital C-star algebra and it has an injective CP order 0 map into the C-star algebra B with image equal to X and image of the unit equal to E, then it turns out that, so we can take the inverse of the identity map. So in this setting, X and X bullet are just equivalent, or well, actually X in full generality just sits densely inside of X bullet. And what we get when we compose the map psi into X sitting inside of B and then back into X sitting inside of X bullet, the composition of these two order 0 maps gives us a genuine star homomorphism that just sort of passes through X as a subspace of B. And its image is actually going to be a dense subspace, so we actually do get a surjective star isomorphism between A and X bullet.
Hey, Kristin, may I ask a question? It's Roy. I have a quick question.
Yeah.
I know I asked this before kind of when you spoke at Purdue, but I quickly again, so if I were to assume X was actually injective, okay, does this bullet, does this pre-C star structure, so this bullet you're defining here coincide with the multiplication that I can say induce on an operator system if it's already injective?
Let me think. So if it's actually, so it's a little bit tricky here because secretly X, you can think of it as an operator system. You have to think of it as an abstract operator system, of course, because it's non-unital in this setting. But it turns out that, yeah, actually in this setting, X bullet is, see, one can realize, I can't remember exactly if I need to throw in 1 or 2 extra criteria on it, but X bullet's actually the enveloping C-star algebra for that abstract operator system.
Ah, okay, that makes sense, because if you recall, yeah, I brought it up, the bullet construction reminds me of how you typically would define, how you would show that an injective operator system that can be necessarily a C-star algebra if you. Right.
Yep.
Excellent.
And that's actually basically how I show that that X bullet is the enveloping C-star algebra.
Yeah.
So if you're comfortable with this notion, then, you know, secretly you can think of X bullet as the enveloping C-star algebra.
Yeah, that's excellent. Thank you.
Yeah. Okay, so we can actually say a lot more. The theorem becomes much more robust when we assume that that subspace that we were working with is closed. So if X was a closed self-adjoint subspace of a C-star algebra and E is a positive contraction sitting in the C-star algebra, then we can say that X is the image of an injective CP order 0 map from some C-star algebra into B. And this is equivalent to saying that X and E satisfy C star. I don't have to throw in this assumption that X is closed in that bullet norm, because remember I mentioned that if X was already closed in B, then it's automatically closed in this bullet norm. So once we assume that X is actually closed in B, we get a much more robust theorem. Oh, that's what I just said. Yeah, so this comes from the fact that X is already closed when X is already closed. And what this means is X is already complete with respect to this bullet norm. Taking this closure doesn't add anything. And so now the identity map between X bullet and X is a CPC order 0 map without any sort of extension. And in fact, we can think of this as a complete order isomorphism by virtue of being an injective CPC order 0 map. Remember, I said that once you know you have an injective CP order 0 map, its inverse is automatically completely positive. So we really, as soon as we have an injective CP order 0 map, we have a very robust correspondence between X bullet and X. Okay, so let's take all this extra structure and take them back to the generalize the notion of the NF systems. First of all, apologies to Wilhelm. I'll mention that this is a working title and we have not agreed on any titles for these systems. Okay, so recall that our goal in all of this stuff with bullet norms and order 0 maps was to relax this asymptotic multiplicativity requirement for NF systems. So, and just to remind you of the definition, an NF system is a sequence of finite dimensional C-star algebras with asymptotically multiplicative, completely positive, contractive connecting maps. But the issue with relaxing asymptotic multiplicativity is that when you lose that, you lose the C-star structure, you lose the algebra structure on the inductive limit. But now we're equipped to overcome this hurdle. So first of all, when one wants to just try to generalize this notion of these NF algebras, a lot of the machinery goes through just the same. If we have a sequence of finite dimensional C-star algebras with CPC connecting maps, we still have induced CPC maps from each of the finite dimensional C-star algebras to the quotient, which, since it's about to make a few more appearances, I'm going to write it as F sub infinity to stand for the quotient of the product mod sum of the FNs. And so we can still think of, we can still form the limit, which is just going to be the closure of the images of these guys inside of F infinity. In particular, this is a closed self-adjoint subspace of the C-star algebra F infinity. So although X might not be a C-star algebra, if we can find some positive contraction in F infinity so that X and E together satisfy the C-star criteria, then secretly X is in a very strong correspondence with a C-star algebra that I can just build out of X by sort of changing the way that I view the elements. Okay, so the task then is to encode these C-star criteria into a system of CPC maps between finite dimensional C-star algebras. Okay, so let me remind, now I have to unpack what C-star was again, because we actually need to encode each of the individual pieces. So we want conditions on the system which guarantee that we have some positive contraction in F infinity so that the limit X together with E satisfy the following. E actually lands in X, not just in F infinity. E commutes with X. X squared is equal to EX, and E is an order unit for X. Okay, so first step, to find a positive contraction E that lands in X and also commutes with X, we're going to look for a sequence of positive elements in the product of the FN, so positive contractions in the product of the FNs, that is asymptotically coherent. So without having to bog everyone down with a lot of technical definitions all at once, just give you a feel for what I want to get out of these definitions. So asymptotic coherence guarantees that when I look at the images of each of these ENs in the induced maps into F infinity, then the sequence of these images becomes Cauchy. And so that means, of course, it's going to have a limit. And the next criteria that I want to put on it is that it's asymptotically central, which is going to be what we need to guarantee that the limit of that Cauchy sequence, let me call it E, actually commutes with X. So with these two criteria, we guarantee that we have some E positive contraction in X that commutes with X. So skipping to the third criteria, to ensure that E is an order unit for X, we also want to require that the sequence En is an asymptotic uniform order unit, which in this case, what we want to guarantee is actually just that if you take any N and any self-adjoint element in Fn, then, and we look at the image of X in this canonical induced map into the quotient algebra, the norm of rho n of X times E dominates rho n of X. So this is just this uniform order unit criterion, but since we have this nice uniformity, the fact that it's an order unit now sort of on this dense subspace, the union of the images of Fn inside of X, this will actually pass to all of X. And so under these assumptions, we get a positive contraction, E that commutes with X, that lands in X and is an order unit for X. So just for the sake of this talk, let's call such a sequence an asymptotically central order unit. So now to get the last criteria, and this is the hardest one to really get, is this X squared equals EX criteria. So now that we have a designated unit, we want our system to capture this unital definition of order 0. And by that, I mean, I'm referring to, again, to the structure theorem of Venter and Zacharias, which says that an order 0 map is multiplicative modulo multiplying by the image of a unit, which in our system is, or in our setting translates to this X squared equals EX criteria. So this is the next thing that I need to encode. And so we arrange for this by requiring that our system be asymptotically order 0, but now with respect to this order unit that I've singled out. And so this condition basically will tell us how to build for any K and any XY and FK, some element in X, which this X, again, this is the closure of the union. So the Z is probably going to end up being a limit of elements that land in this union of the images of Fn. But we can build an element Z that witnesses the fact that rho K of X times rho K of Y is equal to EZ. And it turns out in our setting, this actually ends up being enough to get it for the entire space. And in a sense, this sort of goes back to the uniformity that we imposed on E as an order unit. But one quick remark is that just as with typical order 0 maps, if these maps, these asymptotic order 0 maps are asymptotically unital, meaning this order unit starts to hug very close to the units of the finite dimensional C-star algebras, then the resulting sequence is going to be asymptotically multiplicative. And then we land right back into the classical NF setting of Blackadar and Calgebras. Okay, so now definition, again, working title just for this talk. I've not run this by Wilhelm. So we say a generalized NF system is a sequence of finite dimensional C-star algebras with CPC connecting maps that are asymptotically order 0 with respect to an asymptotically central order unit. So basically, this was built to encode those C-star criteria into the system that will guarantee that the limit X and its order unit E satisfy these C-star criteria, and we can build a C-star algebra. Now it's time to give an example. So example which is creditable to Blackadar and Calgebras sort of through the lens of the work of Venter and Zacharias, but one has to go to Brown, Carrion, and White, and also my work with Wilhelm to actually get some exact statements, but we can say that any separable unital nuclear C-star algebra A admits a CPC approximation, so that if I take the finite dimensional C-star algebras, and then I just take the composition of the maps going from Fn all the way up to further down the line, some Fn, by just following the zigzag of this asymptotically commutative diagram I showed you earlier. And this will form a generalized NF system. So let me talk a little bit about that construction. So, and what I mean by it admits such an inductive system. So we take a CPC approximation of a unital C-star algebra with asymptotically ordered 0 maps. And this is the part that we needed Blackadar-Kirchberg, Venter and Zacharias, or just Brown, Carrion, and White for. And what I mean by asymptotically ordered 0 maps is that before, when we saw the definition of quasi-diagonal, where the downwards maps, the maps from A into the finite dimensional C-star algebras, were approximately or asymptotically multiplicative. Now they asymptotically satisfy this order 0 criteria. If I have such a CPC approximation, then if I look at all of these downwards maps, these psi n's going from A into the finite dimensional C-star algebras, this is going to induce a completely isometric CP order 0 map from A into the C-star algebra F infinity. The same way we've been inducing maps into F infinity all along. So it turns out, after passing to a subsystem, where we impose something, a sort of very highly technical, not highly technical, but a technical assumption that really permeates a lot of the work that we're doing. This, we call it a summability criteria. But after passing to the an appropriate subsystem, we can actually guarantee that the image of psi hits on the nose the inductive limit of these finite dimensional C-star algebras, where we just take the connecting maps to be going through the little zigzag going through A. And the fact that psi is CPC order 0 will imply that the system is asymptotically order 0 with respect to this asymptotically central order unit. In other words, we will have a generalized NF system. Oh yes, and actually, just to make sure, unless it wasn't clear, the image of the unit will be the central order unit for X, as it should be. Okay, so by encoding C-star into our definition of the generalized NF systems, we've guaranteed that the inductive limit, along with this choice E for the order unit, satisfies C-star. And so now we get to say the following. So if we take the inductive limit of the generalized NF system, then it will be completely order isomorphic to a unital C-star algebra, X bullet, in fact, via an injective CPC order 0 map, which actually just looks like the identity map on X bullet. But it's CPC order 0, of course, when we think of it as a map from X bullet into F infinity. Moreover, if A is another unital C-star algebra, and we have some injective CPC order 0 map from A into the C-star algebra F infinity, that maps A to X and maps the unit of A to E, then X is star isomorphic to X bullet. Taking that back to our example, we can actually say that if we took our separable unital nuclear C-star algebra and that CPC approximation that we were guaranteed that forms a generalized NF system, then A is already going to be star isomorphic to X bullet, because psi was an injective CPC order 0 map whose image was X. So in a sense, this construction rebuilds the C-star algebra from our completely positive approximation, or that gave us our completely positive approximation. So now the next natural question is, okay, in general, if we didn't know that our inductive limit came from a completely positive approximation, could we tell that it came from a completely positive approximation? Can we tell when the C-star algebra X bullet associated to a generalized NF system is nuclear? Okay, so here's a picture. At least this is how I sort of visualize what's going on. So we've got this sequence, FNs of finite dimensional C-star algebras, and the induced maps into the limit X. Now, we've arranged it so that X has this nice, robust one-to-one correspondence with X bullet via CPC order 0 map from the C-star algebra X bullet into X. Now notice that actually the inverse image, because the identity map is an injective CPC order 0 map, its inverse is completely positive. Maps positive elements to positive elements, even under matrix amplifications. And so that means that at each stage, if I compose it with the canonical map from Fn into X, then I get CPC maps that go straight from my finite dimensional C-star algebras into X bullet. So let's compress that picture and ignore the X in the middle. And now it's really starting to look a lot like a completely positive approximation. So the question is, can we come up with downwards maps to get a completely positive approximation? And the answer, and I should also put Calgebras' name on this actually, my apologies. So I think this is never really stated explicitly in the literature, but it appears a fair bit in the literature. And we can actually say that if we assume that the upwards maps, these phi-ns, are decomposable into a direct sum of a bounded number of CPC order 0 maps, which you should think, if you've seen any talks on this before, this is the finite nuclear dimension criterion, then the answer is yes. Then we can come up with the downwards maps from just knowing the upwards maps. In general, we don't know the answer. But it turns out we can get around that. So it turns out we can still get nuclearity without the downwards maps by invoking the one-way completely positive approximation property. So for the sake of time, I won't linger on this too long because I certainly don't have time to work through how it applies. This one-way completely positive approximation, this appeared implicitly in work of Ozawa and was fleshed out by Sato. And it gives a characterization for when, if you have these upwards maps, so these maps going from finite dimensional C-star CPC maps going from finite dimensional C-star algebras into your C-star algebra A, when you can then, just from that information, conclude that your C-star algebra is nuclear. And it really has to do with looking at the image of this induced map, capital Phi, and looking at the canonical image of A sitting inside of its so-called sequence algebra, and just making sure that the unit of A is going to land in the image of the unit of the product mod sum quotient here. When one looks at it closely enough, you can see that our structure actually very, very naturally fits into this setting. And this theorem gives us exactly that the C-star algebras are nuclear. But I should give a quick remark. This proof really goes by showing that the double dual of A is hyperfinite, not by constructing the downwards maps. And so we still don't have an argument that a one-way CPAP that really constructs a CPAP. But nonetheless, what we can now say is the inductive limit of a generalized NF system is completely order isomorphic to a unital nuclear C-star algebra, again, via an injective CP order 0 map. So now let's go back to this motivating question. So recall the Blackadar and Calgebras characterization of NF algebras as the separable nuclear quasi-diagonal C-star algebras. Right, so, oh yes, I've quoted exactly the theorem we saw before. So A is nuclear and quasi-diagonal if and only if it's star isomorphic to an NF algebra. And so the thing is that by replacing asymptotic multiplicativity with asymptotic order 0, we can also drop quasi-diagonality. And we get the following. Our equivalent for a separable unidal C-star algebra A is nuclear, and there exists a generalized NF system and an injective CP order 0 map, which remember is a complete order isomorphism, from A into the sequence algebra F infinity that sends A to X and sends the unit of A to E. So really this is, you should think of this as the CPC order 0 analog to a star isomorphism. And so this is really just using the structure of completely positive order 0 maps to take away the necessity of multiplicativity to give us these C-star structures. And with that, I will end. Thank you.
Yeah, thank you very much for a very nice talk. Are there questions?
Yeah, I have a question. Hey, Kristin, it's Roy again. So on that, so going 3 slides back, is that comment by Winter when if you have the upwards maps decompose into a direct sum of bounded maps, is the bounded sufficient precisely because these C-star algebras, these FIs are finite dimensional, as opposed to, I assume they decompose direct sums of say CB maps or N bounded maps or things like this?
So it turns out actually this paper of Brown, Carrion, White that I mentioned a while ago, we actually know that you can always come up with a completely positive approximation of a nuclear C-star algebra where the upwards maps are not direct sums of CPC order 0 maps, but convex combinations of these.
Mm-hmm.
And there's a sense in which what Wilhelm actually was able to pull out of a lot of this previous literature is that when you have this this added orthogonality that comes from taking these direct sums, it really gives you enough space that what's a fast way for me to say this? Okay, so if one actually just assumed just no holds bar that this upwards map was just a completely positive or CPC order 0, then one can actually build an inverse for the CPC order 0 map and then Hahn-Banach it back up to get to the entire C-star algebra. When your upwards map is built out of order 0 maps, you can sort of take each of the order 0 components and come up with these inverse maps. Now, the issue is when you take this sort of generic, Hahn-Banach extension gift from the gods, you don't have much control over what's happening sort of off of the images of the individual CPC order 0 components. And so you sort of, in the case where your maps actually decompose as order 0 maps, you're able to guarantee that you don't have too much noise conflicting. But when they're only convex combinations of order 0 maps, the extensions can interfere with each other too much to give you a genuine approximation.
Mm-hmm, mm-hmm.
And I think, Wilhelm, correct me if there's a better way to put it.
I don't know. It feels a bit unfair that we can't get these that we can't use these local inverses from convex combinations, but at least at this point we can't.
I see.
It's a little bit similar to the fact that when you take nuclear dimension approximations where you have a global bound on the number of order 0 maps, it's very easy to see that finite nuclear dimension passes to quotients,
Mm-hmm.
whereas nuclearity passing to quotients is a very hard theorem. And at least at the moment, one has to go back all the way to injectivity, semi-discreteness.
Mm-hmm, mm-hmm.
Laurent's work, of course.
Okay, here's another obvious question. Well, the big open problem is the universal coefficient theorem. Do you have any idea if your methods could help in that direction?
So I guess this is never really fully outside of one's mind. But right now, the next thing that we really need to be able to do, which we've made a fair bit of progress in, and I don't have the time to talk about it, but when we actually come to looking at these systems, the next thing that one really wants to do is to be able to encode the K-theory and the traces of your C-star algebra actually in the finite dimensional system without ever actually having to pass to the C-star algebra. And yeah, hopefully if that all manages to work out, then, well, I'm not going to make any sort of promises.
And then you also have to incorporate the KK theory or get the KK theory from the system.
Yeah.
Yeah, but at
may
least,
I make a comment?
Yeah.
That's one way to go, to incorporate KK theory, and I'm sure this is possible. But the first test case would be the König formula for tensor products. And for this, you can say something in principle without using KK, and it's one of the motivations for this to try to prove a König formula for tensor products in terms of these systems. But we don't have this yet. But we can describe K theory though.
I mean, for every nuclear C-star algebra, you have a nice, really nice approximation with good algebraic properties. So, I mean, that should help.
Yes, thanks. Thanks for the encouragement.
Okay, so good luck.
This may, I mean, in spirit, it may have a connection to what I'm doing with Rufus. You know, this kind of quantitative or controlled K-homology theory. So that provide an approach to the UCT. I mean, but, you know, the condition we have, it's not clear exactly how it matches, like from your side.
I'm really hoping we'll be able to meet halfway.
Yeah, so because we also have some kind of dimension, like under some finite dimensionalities, and the UCT is true, but it's not clear whether our dimension, your dimension are like, yeah, somehow how it's connected or related, yeah. Yeah, it would be wonderful if one can meet in the middle somewhere.
Right, anything else? Very exciting, all of this.
If I may, I would like to say something what Richard Ness was supposed to say, but his microphone went down. Is it okay? Yeah. So we would like to make an announcement, Richard and I, that tomorrow we start the new semester, the spring semester 2021, with our North Atlantic non-commutative geometry seminar. Tomorrow is the first talk. It will be by Adam Doran from Copenhagen. Operator subsystems, so it's a very operator algebraic talk. And right after the seminar, most of you will get the full schedule of our semester in an email. That's what we wanted to say. Thank you so much.
Right, thank you. And some other maybe questions, there's still some time.
Yeah, I have
related to the talk, I would say. Yeah.
Kristin, I just wanted to ask a quick question about order zero maps. And it's not really a very precise question, but if you were to look at the set of order zero maps within, or completely positive order zero maps within just all completely positive maps, how common are they? So if I had a dartboard full of all the completely positive maps and I threw a dart at it, is it like?
Yeah, I mean, I would say without anything that I could really bolster it, any good theorems to bolster it with, that you would probably not hit an order zero map. These are very, very, very nicely behaved, much like the star homomorphisms. but yeah, yeah, in general, guaranteeing that something is going to be an order 0 map versus CP. Actually, so what I can tell you is probably the best way to go to really compare the two is the structure theorem that Wilhelm and Zacharias give for these completely positive order 0 maps, and compare this to, say, a Stein spring dilation type theorem for CP maps. And this sort of gives you a good feeling of when you can say you have an order 0 map versus when you can say you have these just plain old CPC maps.
Okay, cool. Thank you very much.
Okay, so I think that's about it. I don't see other questions. Right, let me thank you again for a wonderful talk. And so then there is the usual virtual applause, of course. And let me just repeat that next week, the seminar will take place on Wednesdays, 2 o'clock. Just so that you know, it's also on the website. And hope to see you then. Bye-bye.
Kristin, thank you for the talk. Once again, it was very nice, very nice. I liked it.
Thanks, Roy.
Cheers. Bye-bye.